Okay, hello everyone. For the internet of verifiable applications. And yeah, let's get right into it. So what is Mina Protocol? How do you think about that? It's the internet of verifiable applications. So what is exactly this step from trustless to verifiable? Basically, kind of you could execute code in like a global network without trusting anyone to actually execute the code correctly. So when we now make the step to verifiable, we actually want to do exactly that, but in a very succinct and efficient manner. Environments will execute our code in a trustless manner, and anyone actually can verify that in a super nice way. All right, so what concrete step did Mina now take to actually facilitate that? So until now, kind of blockchain had their native execution environments replicated. What does replicated mean? In order for anyone to verify what they do, download all the data, all the transactions that went in, and execute them themselves to make sure the result is the same and therefore it can be trusted and verified. So every active network participant had to do that. And that obviously scales very badly. So what Mina did is we took that model that instead of everyone having to execute the same thing, only the ones that are interested in actually knowing what that particular computation was have to execute it. And all the other ones can verify a succinct proof of all the work that's ever been happened and make sure that basically that allows them to basically accept the state of the network. Examples for replicated execution environments are like Ethereum, Solana allows us to do that. And in short, that's zero knowledge proofs. In our case, that's Kimchi. Kimchi is our proof system, and we can use that to actually build the executed and proved and combine them together in one single proof. So we can kind of fold everything together in one succinct kind of package that doesn't depend on the size of execution that went into it. And it has three basic properties. The first is distributable, so keep that to a lot of like participants, and all of them can verify that statement in a very quick and cheap manner. It's also privacy enabled. So since we're talking about zero knowledge proofs, and one of the side effects that technology gave us was that we can actually do private computation and make it verifiable afterwards, which allows us to like not leak any data to like a blockchain environment, to a public network, in case we wanted to stay private. And the third property, as I've already touched upon previously, it's very succinct. So basically means that no matter how much code execution you try to prove, the proof of that and the verification or the cost of verification it takes to actually verify that is constant size. So it doesn't change as that. And what we made with Kimchi is we basically said, okay, that execution can be a blockchain. And so we basically made the whole blockchain one single size proof. And that means that basically the longer the chain gets, in traditional blockchain, the state grows, the amount it takes to verify that blockchain also grows. The blockchain and all the data, the current state, is valid without actually having to rerun all of that. Awesome. So if we have this trustless operation that allows us to actually prove and then verify any computation on any machine in a trustless manner, so why do we need consensus? Consensus we need for basically three things. One is finality. That property basically says, okay, any computation that you made, if you operate on like a global state that you guys or that anyone kind of wants to agree to, then finality says at some point I can make sure that that computation is actually something we call canonical, basically meaning it cannot be rolled like a shared database or like a blockchain. We want to make sure that anyone can actually participate. So what censorship resistance gives us is that no single party or no bigger group of parties can actually control what goes into the blockchain and what doesn't go into the blockchain. As I mentioned, we are operating on like a shared database on a global state, and what consensus gives it actually coordinates and synchronizes those operations in like a concise manner. Yes. All right, so that consensus stuff, that's not new. That has been around for 10 years or more with all the blockchains that are out there. So what makes our consensus, which is verification-based, special? The first thing is we save a lot on execution verification. Previously, I already said that two times, I think, we don't have to verify all the stuff that went into the blockchain. We can actually verify a single proof of that and kind of one succinct proof. Everything that goes into that will also become part of that succinct proof. That means that having that, I can actually verify any, and that in the end enables decentralization at scale. We can scale that system because our hardware requirements and other things don't depend on the amount of computation that happens. It stays the same, and therefore like anyone can participate, and it's super easy to join the network. Awesome. Just to summarize, Mina Protocol kind of enables a verifiable execution environment, and what building on Mina is by separating that architectural models into the application layer and the base layer. So we already talked about like decentralization properties, and we can build on top of that. And the application layer is exactly that, what gets built on top of data, and yeah, do stuff like that. That happens on the application layer. Okay. All right, let's look at how the application layer works in this case. So what we want to achieve is verifiable and distributed computation that scales, and there are three components to that. The application layer, in our case, relies on something off-chain, and we then commit a proof of that computation has been run honestly to the blockchain back, and therefore can verify that everything we did was actually valid. This enables us to like not be dependent on any gas costs or any like block size limit or anything like that, because we can put as much computation as we want into that single proof, and then let the blockchain verify it. Also, all are application as well. So you can kind of think of this model of like public and private computation. They kind of marry into each other on the application layer. So you can have stuff private on your client side, phone or whatever. You can prove it, you can execute it, and then combine it with some public execution that kind of coordinates execution. You can build anything you want. It can have any like, it can have any logic. It can have any architecture. It's not like I don't know, restricted by like any smart contract model or bytecode or whatever the fuck. In a great manner. It also does proof accumulations, as I've mentioned. Basically, all applications become part of that succinct proof. It also does, it accumulates it. Basically verifies proof within proof, and therefore kind of comes to that like proof singularity. And also, the base layer gives us interoperability between those provable applications that we build on the application layer. We need some way to kind of, for them to interact with each other, and that is what the base layer gives us. So the primitives that we have available at the base layer for actually achieving that are threefold. We have shared sequencing. So the Mina protocol is kind of this action reducer pattern, we call it, embedded, which basically gives us shared sequencing. So basically users can use that as like the central liquidity layer, so that we don't have liquidity fragmentation over like many layer 2s. We can have them in one place and then actually interact with them that way. And the last part is verifiable settlement. So applications, this is kind of just the way we kind of think of kind of drawing that up. At the top, we have the base layer that verifies our proofs. We have things like settlement. We can build our application in. And those, as I've already said, can have like a kind of multiple phases, right? They can be like rollups, they can be MPC stuff, they can be like peer-to-peer multi-party protocols, yeah, stuff like that. And the way those kind of interact with each other is by settlement, and basically kind of the from the base layer. All right, let's look at how we can actually build those verifiable applications. So how do we build on Mina Protocol? Just to kind of give you like circuits basically means your application, your business logic, everything that you write will get compiled to a circuit, and that circuit is the thing that we can actually prove. They have some restrictions. They have like some properties that we have to think about when building. The L that we use to build kimchi proofs, and it's built by Owen Labs, and it's TypeScript SDK that people can use to actually write circuits. And we use it under the hood as well, so that's something we have to think about. And then we have this concept of public and private inputs, also outputs. And what that means is basically, if I have a program, I have inputs to the program, and I have some outputs from the program. And we can kind of decide as a developer if we want a certain part of those inputs to be public and another part to be private. And what that enables us is exactly that. privacy enabling, client-side proving. All right, let's look at some simple example of how we can actually write a circuit. So here is one to that and creates a proof that it correctly added one. And as an output, it outputs the new counter. And the syntax we use for that is called zkApp program. It's kind of the construct that we use to build circuits within OpenJS. And so the first thing we do as the counter state, that's the state we define. We say it has one value, it's a U64, that means it's 60. We define the inputs and the outputs. Then we define one method in our case, it's called increment, and it does a very simple thing. It receives that's the thing in the method function. It receives the state, it computes over that state. In our case, basically 2 steps. And the first thing is we need to actually take that zkApp program and compile it. That means under the hood, it basically translates that into that circuit, takes the zkApp program that we created, call our function, which is called increment, with the input state. And that's an asynchronous operation. It takes a few seconds. And after that, we receive the proof out of that, which we can then, under there, use to verify that proof and see if it's valid or not. And that verified return value that we get from there is a Boolean saying true if it's a circuit. That's a circuit that does something. It's kind of on its own. It doesn't really interact. So how can we now kind of go from this simple circuit to building actual zk application chains where multiple users can interact with each other, where we can build our applications that users can use. Multi-user applications that then run on the blockchain. And yeah, under the hood it's powered by OpenJS, so all the base building blocks that we use and also how the business logic is written is using OpenJS and the primitives that OpenJS gives us. Protokit is end-to-end, so there's no one that can actually or maliciously influence the result of any computation. Everything is kind of proven in primitives, so we try to kind of make the framework as powerful and versatile as possible. So you have a lot of tools that you can work with that actually help you with building those applications and abstract over a few things that are more complicated and tedious too. Why do we need an R sequencer? And the reason why the question is here is that Protokit has to be run by someone. Someone has to prove the code execution. Someone actually has to run the application to generate the proofs. Therefore, that's some party, right? Why do we need that? The reason is execution orchestration. Proving is a tedious task, and also executing everyone's transaction in I don't know, sequenced manner is also something that's not very easy, especially when you only have circuit writing tools and some protocol that Mina offers. So that's why we build Protokit. We want to make that as easy as possible. All right, so how does the zk application chain work in practice? So it's based on validity proofs. That means that, again, everything end-to-end is proven, but compared to other, that again leads to that there's no sequencer operator malleability. So if you are the party that actually executes your application, you have no way of kind of influencing the result. And then we separated and those kind of give us different tools which we can work with. Most applications will be built in the runtime. So that basically says, okay, what does your application do? And in the protocol, you can customize how the chain behaves under the hood. So I don't know, are there nonces, how are fields handled, stuff like that goes in the protocol. And then the sequencer is everything that goes on API level, interacting with databases, stuff like that. Awesome. So how does this zk application chain work under the hood? So we have a pretty simple workflow, I would say. So it's kind of the intent to do something. I want to swap this token for this token on a DEX. And users authorize those signatures, those transactions by a signature. So they sign the stuff that they want to do, therefore we can make sure it actually came from them. And all right, next thing, the transaction lands in a mempool. So the sequencer, the one that operates the app chain, keeps track transitions are emitted. What are state transitions? Basically, they mean since we all basically the application operates in a global state, transactions that come in and get executed can change that state. They can write to it, they can read from it, And every 10 seconds or whatever you configure it, they will collect it into a block. So the block is kind of the primitive that gives us those containers of multiple transactions, and therefore kind of allowing us to, iteratively basically continue run. Just to again go quickly through it. Alice here on the top left, she submits a transaction to the application chain's mempool. The sequencer picks up the transactions, executes them. As part of executing, it will emit an array of state transitions. Those are executed by the protocol and then applied to like the global state. All of that is proven end to end. Therefore, like we receive a transaction proof. We bundle multiple of those transaction proofs together in a block proof, and that block proof goes to the base layer. In our case, Mina, and gets verified there. Then the whole cycle starts again. Awesome. What else can Protokit do apart from just writing super simple stateful applications? It can do token bridging. It goes out of the base, out of the box with settlement. We have an archive node and a sequencer, or archive node implementation that basically allows you to index all of the stuff that goes on your chain. We also have a framework for processing that data and basically giving like historical, infographics, or have like a framework for doing that. We do proof parallelization out of the box so that stuff actually gets executed very fast. We also have DevOps and Docker integrations. Awesome, so let's build it. Let's see how the code looks. For us, it all starts with the starter kit. So that's a repo on GitHub. You can git clone that or use dgit and clone that on your machine. What do you get from that starter kit? Basically, a few things. The big chunk of your work will probably be in the runtime, and that is part of an app chain. So basically that is what lives on the packages chain source, and there you can build your applications, configure your sequencer, do stuff like that. So all the logic goes into the app chain. What also comes out of the box is a pre-built UI. So it gives you kind of a rough skeleton of the UI, how you can like connect your wallet, connect to the sequencer, basically have all those front and back end interaction. We kind of build a template for that. All right, so that's basically what comes with the starter kit. How can we run it after we build the application? We can, obviously the first thing is we have to do, we need to install our dependencies. After that we can call p-npm dev, and it will spin up the UI, it will spin up the sequencer, hot reload, stuff like that. How does the UI look? That's how it looks. It basically gives you that skeleton that I talked about with a faucet. The first thing you have to do is you connect your wallet. In our case, our wallet, which is like the predominant wallet for Mina. You connect it. After you did that, on the right top, stuff will be updated there. Okay. How can we build a runtime module? So basically, runtime modules are the way we build applications and how we structure them. You can think of them like classes or like smart contracts on Solidity, stuff like that. Basically, it's built out of three things. It has a class-based definition. It has stateful properties, so state that you can write different things. You can choose to execute or not execute. We'll see how that works later. Let's build kind of a minimal example of the structures. So we have a proposal ID, and we have a struct to actually collect all the votes that we did. So kind of a number that says how much voted yes, how much voted no, and then a proposal consists of a recipient, an amount, and the votes that have already been cast. All right, so the runtime module, let's quickly go over that. The first thing we do is we define state on the runtime module. So as you can see, coming back to like the class, our framework picks it up, and then you can define state like we see here. So in our case, we create a state map. Basically means kind of a mapping from like a number, in our case, to that actual proposal. We can call state map.from. We assign it to our instance variable. Basically, in our case, says, okay, what is the address of the treasury? Where does that money live? All right. Also important, we have to inject the dependency in our case, which is the balances module. It basically keeps tracks of all the balances that all the accounts have on the app chain. Then we can create a runtime method. Basically, in our case, what we do is we want the user to be able to vote. and they vote for a specific proposal. Yeah, we can go into the code. Basically, it's ONJS code. You should see all the, or find all the examples in our repositories. It's a very intuitive way to actually write stateful applications. The state kind of gives us get and set methods, so we can actually get and set state, our documentation as well. Another method, executing a proposal in case it passed. All right, we can also write tests. We use Jest for that. It's like a native TypeScript framework. We have like some utilities for that to actually test your code. Create like unit tests for your methods, see if they behave right. All right. You'll also find a lot of Mina team members around the conference if you have any questions. Also, the slides should be available in the QR. Any questions? If you want to try to build on Mina, we'll talk about the prizes later on stage. So yeah, thanks for listening.